Swayam Prabha. Digital India. Educated India.
So, we will continue with the significant test of variability. So, next problem is that the nominal standard deviation of a Lee strength of ring yarn is 2.5 pound, but a sample of 15 bobbins when tested, the standard deviation of a sample is found to be 5 pound. So, here first we have to calculate the, we will calculate the F value, then we will try to test using the F test, and subsequently we will verify this with the standard deviation also. Now, 2.5 and 5, these are the two data. As we know, we have discussed F value will be, this will be numerator 5 and denominator will be 2.5. We can say this is V1 by V2, V1 means 5 square, V2 is 2.5 square. So, that way we can calculate the variance and which is 4. So, F variance ratio is 4 we have got. So, let us see in the similar way. Now, numerator always it gives the whatever number, the degree of freedom of numerator is termed as gamma 1 and degree of freedom of denominator is termed gamma 2. So, numerator here is the sample. So, sample is based on 15 bobbins. So, the degree of freedom will be 14, and here large sample degree of freedom will be infinite. So, what we have to see, we have to refer to the T table, F table with 14 against 14 and infinite. 14 will be in horizontal side and infinite will be in the vertical side. Let us see the, refer to the F table. F table, if you see here, so infinite is gamma 1 and 14. So, it is coming around 2.13, and in 99% level, so 14 it is 3.00. So, 3.00 and 2.13, which these are less than our calculated value. So, we can conclude that this values are, this difference is significant. 2.5 and 5, the difference is significant. Similarly, if we calculate based on the standard deviation, the T test, if we do, if we try to test the T test, so we should get the similar result, similar conclusion. So, because here we have at least one smaller sample, so we can very well perform the F test, which is easier. Now let us try to see the t test value. So standard error of standard deviation. So what is the, this is the nominal value, so that definitely it will be the standard deviation of population, and then under root number of sample 15 multiplied by 2n, so it will become 0.45. 0.45 is the standard error of standard deviation. Now let us calculate the t value. T will be, so 2.5 minus 5 divided by standard error 0.45. So 2.5 divided by 0.45, this will be 5.5. So this is higher than the table t value that we can check from the t test. So again our conclusion is that it's a significant. So here the value is not that important. What is the t value we are getting? If it is more than that, then it's a significant. Okay, even so it's a at what extent we are not bothered. If it is more than 99% level of t value, then we can consider it as significant. Okay. Now next one, significance test for dispersion for single standard deviation with small sample using F test. So this also already we have done. Now let us see the nominal standard deviation of the Lee strength of a ring yarn is 3.2 pound. But a sample of 13 bobbins from a lot is tested. So nominal, that is population standard deviation population is 3.2, that is, and n is 13. We have tested 13 bobbins and we have got the standard deviation sample is 4. Now we have to test whether this is actually producing the significant result or not. So nominal is lower than the sample, so the F value will be 4 square by 3.2 square. So that we can calculate straight away the F value. Four square by, so we have got the F value 1.56. Now here this is a nominal, where nominal is coming into the denominator. So the gamma 2 will be the degree of freedom 2, which will go vertically, which will it's infinite, and for numerator it's a sample 1 which means it will be 13 minus 1, 12. So we will check the value of 1.5. So if test we have to do, so degree of freedom we have to calculate. So 12 and infinite. Okay, so infinite will be that this is as it is in the denominator. So gamma 2 will be infinite. So we will refer to the T table, and as per the T table, we are referring to the F table. As per the F table, the values with 12 against infinite, it is coming 1.75, and 1.75 is, and for at 99% level it is 2.18 from the T table we can get. And what we can see that 1.56, the F value we have got, which is less than 1.75 and 2.18. So we can conclude that there is insignificant evidence to prove that variability of the yarn is greater than usual at both these two levels, 95 and 99% level. So here in this situation, the variabilities are not significant. Okay, so 3.2 and 4. Now let us try to solve it using the T test. Okay, T test we can perform here. So number of sample here, its N is 13, number of data. And nominal standard deviation is, that is population standard deviation is 3.2. So standard deviation of, standard error of standard deviation equal to 3.2 population standard deviation divided by under root 2 multiplied by 13. What we are getting? 0.65, 0.62. If we calculate this, (0.62) is the standard error of standard deviation. Okay. Now, if we try to calculate the T value will be 3.2 minus 4 divided by 0.62, 0.8 divided by 0.62. It is coming out to 1.29. T value is 1.29 you are getting, and what we have to do, we have to check the T value against the degree of freedom n minus 1, that is 12. For 12, so 1.29 is our value. Let us try to see the t value. So t value will be, if we see the t value, if we check the t value for 12, t value is 2.17 and 3.05. So 2.17 and 3.05, and we have got the t value as 1.29. We are at the numerical, this numerical. No. We are at the numerical 2.14. So here if you see, 1.29 was the our t value, calculated value, but table t value is more than this. So table t value was more than this calculated t value, so that again using t test we can confirm that this difference is not significant. So we can use either f test or t test, where t test is more general, we can use in everywhere, but f test, as we have discussed, it has certain limitations. So we can, with that limitation, we can use, limitations are, it has to be used in smaller sample, at least one sample should be smaller, both the samples cannot be large samples. Okay. Now our next numerical will be, so this is, there is insufficient evidence was there, and this we have proved using the t test also. So these are the f table, so one can refer to this f table. Now our next numerical is that we have two ring frames, they are producing 60 Ne cotton yarn, and 50 tests were made on the ring frame A and 70 tests were made on the ring frame B, and we have got the following data. So 50 and 70, and mean count was, so targeted count was 60, and ring frame A is producing 59.24 count, and ring frame B is producing little bit finer one, and standard deviations are given. Now what we have to calculate, is there a real difference between yarn in terms of count and in terms of variability in count. So 60 was the target, and what we are doing, we are testing the, for 50 samples for ring frame A, 70 samples for ring frame B. Now why do you need this type of test? First let us do it, then I will discuss. If suppose we are not considering this type of test, we are testing say yarn A, ring frame A we are testing, and we are comparing with the nominal value. If we compare with the nominal value, let us see what happens. Now, so 59.24. What will be the standard error? Standard error will be 5.3 standard deviation divided by under root 50. Standard error will be 5.3 divided by under root 50. It will be 0.74. Okay, and t value will be 60 minus 59.24 divided by 0.74, 1.02. So eliminating this ring frame B, we are producing yarn ring, we are testing from ring frame A. We have taken the random sample of 50 bobbins, okay, and we have tested the yarn count, and we have got the little bit finer because it's a coarser. 60 count is the target, 59.24 is the little bit coarser. But when we are testing that significance test, and 1.02 is less than 1.96, which is 95% level, and 2.58 are the levels for 99%. These are less than the table T value. We are concluding that this is not significant. So this value is not significant. Now, so we should be happy. We are happy with that conclusion that this is not producing, that ring frame A is not producing the insignificant difference. Now let us try to see for ring frame B. Standard error will be 6.5 divided by under root 70. It is coming out to 0.77. Okay, 0.77, and t value what we are getting, that 60.25 minus 60 divided by 0.77, and it is coming out 0.25 by 0.77, it will be 0.32. So 0.32 is definitely less than the table value of 1.96 or 2.58. These are the, so we are also happy with the fact that we are producing perfect yarn without any significant difference. But this is wrong, because here we should remember the difference between these two. One is producing finer and one is producing coarser yarn, and we are going to use in a same lot, as a same lot. It's not ring frame 1 is a different lot, ring frame 2 is a, ring frame B is a separate lot, but we are going to mix. For that we are testing the significance difference between the two means irrespective of the nominal value. So if we see for the count, if we try to see here, so standard error of mean is 0.74. So 5.3 was there, and standard error of mean for yarn B, it's 0.776. And then next step is that we have to calculate the standard error of difference between mean. This is the standard error of difference between mean. So this value is under root standard error 1 square plus under standard error 2 square. So it is coming out to be 1.07, and t value as we have done earlier. So t can be calculated using the difference in mean divided by standard error. So difference in mean is 59.24 minus 60.25 divided by 1.07, and it is coming 0.943, and which is again less than the table value of 1.96 and 2.58. So in this case situation we are safe. We are safe because there is no significant difference between these two samples. Now there may be a situation, I will just little bit try to reframe this question. Little bit. Let us try to see for mean. So what we are doing, we are trying to increase little bit the range. So 59, and here it's a 61. 59 and 61, just this much change we are doing. Now if we see between this nominal and yarn A, the t value will be, standard error will be, what is the standard error? 5.3 divided by under root 50, standard error of A, standard error of mean of A 0.74, and t value will be 60 minus 59 by so let us see, we let us make it not 59, so be little bit it's a 58.5 and here 61.5. okay, so it will be 50 by 58 minus 58.5, so 1.5 divided by 0.74, 2.02. okay, 2.02. So 2.02, it's significant in 95% level but insignificant in the 99% level. 99% level, it's insignificant because t value we are comparing with 1.96 and 2.58. so this is insignificant effectively, we can go on running. Similarly, with the 61.5, if we see the standard error of mean will be the 61.5 the 61.25, say 61.25, 61.25 will be standard error will be 6.5 divided by under root 70, 0.74, 77, 0.77, and t value will be, that is 1.25 divided by 0.77, 1.62. So this is insignificant. So in both the cases the difference is insignificant, but if we try to test the difference between yarn A and yarn B, then the real situation will be clear. The problem here will be clear. So standard error 1, what is the standard error 1 will be 5.3 divided by under root 50, and standard error of A and B 6.5 divided by under root 50. For A, the standard error will be 0.74 and for B 0.77. Sorry, it should be 70. Sorry, it should be 70. Okay, 0.77. So if we calculate the standard error of difference under root 0.74 square plus 0.7777 square, it will be 1.06. Okay. Now the t value will be 61.25 minus 50 8.5 divided by 1.06, 2.59. So we can see that 2.59 is more than 2.58. So this value is significant. So when we are producing the yarn of say n number of ring frames, at 100 ring frames, there we cannot test the yarn from a particular ring frame and test the significance. And what we have already discussed, that we have to take the randomly for different ring frames, different samples from different zones, then we can carry out the test. That is one approach, but this type of problem, ring frame A and ring frame B, so between two ring frames we do only when we have encountered some problems, previous problem. Suppose what we have, the yarn, one ring frame is having some problem and the maintenance was done, and to check the variability, so we should not first immediately mix with the lot. So we have to test the significance between some ring frames, then only we can consider it as a bulk running. Okay. So this type of problem we can solve in the industry. Now here let us test for the variability. So significant difference between the variability 5.3 and 6.5. Here if you see here, significance of test of variability in the mean. So first step, we have to calculate the standard error of the standard deviation. So for standard deviation for yarn 1, it will be 0.53 by under 2n, and for yarn 2, as there are 70 samples, so 6.5 divided by under root 140, so 549. So after that, again usually we have to calculate the standard error of difference. So using the same relationship, standard error of difference, so the value comes out to be 0.763. So this standard of error of difference is calculated, and difference of deviation, D stands for the deviation, standard SD, standard deviation. Okay, and then we should calculate the T value. T value is calculated, so standard nominal value is given, so not nominal, for yarn 1, yarn 2 it's given, so 5.3 and 6.5 are the values. So we have got the standard, the T value based on the standard deviation. And then if we compare, so these are the large sample, so the T value gives 1.96 and 2.54. so this T value, calculated T value, is less than the table T value, so that we can conclude that this variability is insignificant. Okay, that is the which is lower, it's not significant. So this is the final conclusion of this type of this numerical. The next is the numerical is that the nominal count of a yarn is 40 NE. Now, when a sample of 20 ring bobbin is tested from a ring frame, the mean count is found to be 41.5. So 40 is the nominal, so we have got little bit finer count. Now, with a CV of count is 2.25%. Now, what we have to conclude, we have to actually judge whether the ring frame is really producing a off count, means whether it's as at in this case it's a finer count, whether this 41.5 count is really finer than the 40 count. So we know that for this, it's as it is difference between mean, so we have to test the t-test, test of significance. So for t-test, we need to calculate the standard error of mean. Standard error of mean, the relationship is that standard deviation by under root number of sample. But here in this numerical, standard deviation is not given, but instead coefficient of variation is given, and coefficient with the count CV, the coefficient of variation of yarn count, that is mean coefficient of yarn count. So nominal count is 40, and when the sample of 20 ring bobbins are tested from a ring frame, the mean count is found to be 41.5 NE with count CV 2.5. So 41.5 is the count and count CV is 2.25. So CV percent is equal to standard deviation by mean multiplied by 100. So CV is given 2.25. So standard deviation we want to calculate, mean is given 41.5 and then 100, so 2.25. So this way we can calculate the standard deviation. So first our idea is to calculate the standard deviation first the which is required for calculating the standard of error. So you can see for sample mean is 41.5, so CB is 2.25 given. So from there we can calculate the standard deviation, which is 0.933. So 41.5, as we know, it's a mean. 0.933 is the standard deviation of the sample, and nominal count is 40. So here we can calculate the standard error. So 0.933 divided by under root number of sample 20. So standard error we can calculate. This is under root 20, 0.208 is the standard error of mean. Now we have to calculate the t value. T value is calculated here. This is a nominal count, the calculated value, and standard error we have already calculated. So T value is 7.21. 7.21 is the T value, and here we can conclude that, so with the n is 20, so 19 is the degree of freedom, and where this value, when we compare with this step with the table value, let us see the table value. 19 is our reading. With the 19, it's 2.03 and 2.093 and 2.86. 2.093 and 2.86. So this value is more than the table value, so it's a highly significant. So this is our conclusion. So it is too fine. Now let us see this problem in other way. So 40 and 41.5. So we are concluding it's too fine. Okay. Now suppose here the variability is very high. The data is same, 40, 41.5 and 20 ring bobbins are there. We have got the mean value, but here instead of 2.25, what we are getting, the CV% is say 7.5%. CV% is 7.5%. So standard deviation, what we will get here, 7.5 multiplied by 41.5 divided by 100. That means 3.11. This is the standard deviation. And based on this standard deviation, keeping everything same, what we can do here, 3.11, we are using, this is 3.11, so standard error will be 0.69. 0.69 is our standard error. Now here we are using 0.69. It's becoming 2.17. Earlier it was T was 2.72, now it has become 2.17. Now the things, what is our conclusion? Conclusion is that the difference is not significant, because 2.17 is less than the table value of 2.86 for that thing. And all this is 95% is okay, that I can also make it, I can make it 10%, variability 10%. Let us see another, let us do it once. In place of 7.5%, let us make it much more variable, 10%. 10% variable. So for 10% variable, very high variability, now let us try to solve. %. So it will be 4.15. 4.15 is the standard deviation, and standard error will be, in this case, 4.15 divided by under root 20, 0.92. 0.92, and keeping all the same condition, 0.92. So here 0.92. So t value will be 1.63, which is less than the value of 2.093 and 2.86. That means the difference is insignificant. What we have done? We have not done anything. The readings are same. What we have done here, the only changes is the variability. In place of 2.25%, the variability is, and that is, so you are producing the same finer yarn with much inferior quality, and our statistical conclusion is that we are not producing finer one. This is basically it's a problem of interpretation. That's why we should not only concentrate on a mean value. We should concentrate on the standard variability. If we see the variability is very high, then the meaning of mean value, its basic importance of mean value is actually it's lower. We should not be considering that it's a good quality product, although we are producing that within the significant chain. So this is very important, interesting problem. So the bottom line is that for any conclusion, we have to consider both the mean and variability, and the impact of variability is much high. Okay. Now our next problem would be that number of readings, how many samples we have to test. Okay. So number of samples, so we have to test, suppose ideally if we test entire population, we will get the most correct result, but entire population testing is not possible. So we have to take the sample, and we should calculate that the minimum number of samples required to achieve certain confidence interval, confidence level. Okay. Now, how many readings of yarn of 30 NE need to be tested to reduce the range of confidence interval to 1/4 of the present range with 30 readings, both 99 and 95% confidence. Now let us see, this is the sampling distribution. Sample distribution is this. Okay, here this is the mean value, and for based on 30 readings, this is the confidence level. Okay, confidence interval. Here it's a T into AC, as we know, plus, and this is minus T into AC, standard error. So present limit is this. Let us say this range is X. No, sir, we will not say A. R1. Present range is R1. And this range we have achieved based on 30 readings, N equal to 30. And if we increase the number of reading, our data will be like. So number of readings if we increase, we can reduce the confidence interval. So our idea is to reduce the confidence interval R2, which is 1/4 of the R1. That is the condition. Now let us try to solve. At 95% level, so present range of confidence R1 is 1.96 at 95% level, and when we are talking about the large sample, 1.96 into AC1, T into AC1. Okay, this is the plus side. So 1.96 AC1 means standard deviation by under root N1, where N1 is 30. So N1 is 30. Now what we have to do, and why we are multiplying by 2? Because in the we are trying to see the both sides. This is T into AC. This side also T into, so this will be 2 into TAC, double. Okay, and R2 will be new range of confidence, will be N, that standard error of 2, it will be multiplied by 2 again. So as it is 95% level, it will be 1.96 into 2 and standard deviation divided by n2 is the new number of sample which is required. Now the problem is simple, so everything is known here. The SD in both the cases will be same, it will cancel out, and the another condition which is given, R2 is equal to R1 by 4 times reduction. N1 is given 30. So simple thing is we have to calculate the N2. So this will get cancelled, this term will get cancelled, is standard deviation will get cancelled. Only the thing is that 1 by n, 1 4 by, so n2 equal to 16 multiplied by 30. So we should remember here, without any calculation we can do it. If we want to reduce it to 1/4 time, so we will multiply this number, present number, with the square of that value. So if it is half, you want to do half, so it will be 30 multiplied by 2 square, it will be 120. Okay, 4 times of that. This is 480. Now coming to the level 99% level, the things will be exactly same, only thing the difference will be, in 99% level it is t value is 2.58, and as it is 2.58, this will get cancelled out using the same formula. Effectively we should get the same result. So 19, so after getting cancelled out, and this 16 comes, as I have mentioned, it's 4 times of the square of this value, and we are getting 480. So irrespective of the level, confidence level, we will get the same number. So for confidence level doesn't matter here. The only thing is that, so then if we want to reduce that error or reduce the confidence interval, then we have to multiply by square of that term. So we will stop here. We will continue with this discussion in the next class. Thank you.